Hello and welcome to Week 8, Lecture 2 of CO 442642 Graph Theory. Today we'll be discussing more on connectivity and minors. So what we'll be discussing today is a number of questions relating to minors, average degree, subdivisions, connectivity, and chromatic number, fundamental questions in the field and the answers that have been developed over the years. So let's start with minors and average degree. So here's a very nice question. Does large average degree force a large complete minor? So as you might see from the graph minor structure theorem, you would think the answer is yes. That the structure of such graphs we know implies in a way that they should have kind of low average degree. And this indeed is true in a much more tighter sense than the graph minor structure theorem gives. Kostochka and Thomason independently in the early 80s showed that if G has an average degree of t root log t, then G contains a kt minor. Now there were some earlier bounds by Motter showing that some function worked, and this is actually the best, up to the order, the correct function. So we'll learn that maybe when we talk about probabilistic methods. So if you take random graphs on that number of order vertices, they don't necessarily have kt minors. And so this would be tight. So that's a very nice and fundamental result. And maybe our first taste of a question that would be natural in the field of graph theory called extremal graph theory, asking kind of what's the maximum number of edges you can have in a kt minor free graph. This would also answer that question. But here I phrased it as, when does large average degree, does it force a large complete minor? So that's maybe the first question. We won't go through the proof of that. There's some different proofs, but essentially a mix of probabilistic methods and maybe some structural. Thomason actually in 2001 figured out the exact constant that goes there. Another question you might ask is, does large average degree force a large complete subdivision? So maybe we want to ask for more instead of just a minor, a subdivision. And this was also answered. So there were various bounds. We won't go through all the history, but the correct bound is by Bollabas and Thomason, which showed that if G has average degree omega t squared, then G contains a subdivision of kt. And that was from 1998. So again, another nice result, but somehow you need more average degree, more edges to really build this subdivision. Okay, so those are some fundamental questions, and we won't go exactly through the proofs. The Bollabas-Thomason one I'll hint at how you could prove it when we get to a later theorem. In the meantime, let me ask an even older question is, does large average degree force a subgraph of large connectivity? So we've seen that large average degree gives you large complete minors, large subdivisions. So now you might ask similarly, well, what about large connectivity? Of course, not for the whole graph, right? Because you could just have some isolated vertices and such, but really, can you do it, find a subgraph? And the answer is yes. So to do that, let me state the theorem with the notion of density. So let the density of a graph G denoted dg be the edges of G over V of G. And then here's this classical theorem of Motter from 1972 that if G is a graph with density at least 2k, then G contains a k+1 connected subgraph H whose density is actually at least the density of G minus k. So in particular, if you have average degree at least 4k, then it's because density is half the average degree, then you get a k+1 connected subgraph. And really, if you just want a k+1 connected subgraph, you can get that with a small cost in density. So if the density of G is even much, much higher, you can always find it at a small cost of density. So that is a nice theorem, and let's go ahead and prove it. So if you haven't seen this before, it's a nice proof that's reminiscent of the other proofs in this discussion today in this lecture. So let's go through that. So the proof is let's just let gamma denote the density of G. That'll just be for notational kind of convenience purposes. Not have to write d of G everywhere. And let H be a subgraph of G such that, so we're going to take a subgraph and we're going to choose it again in the right way. So we're going to choose a subgraph where the number of vertices is at least 2k, which of course is kind of possible because G does. We're going to also choose it where the number of edges is strictly greater than gamma times V of H minus K. So good. And then we're going to, subject to those conditions, choose it such that V of H is minimized. And we note that such H exists since G is such a graph. G has at least that number of vertices, and the number of edges is actually gamma times V of H, and so, gamma is at least 1. This is fine. Okay, so now we've done with that. Now we continue on. So now what? So we have this subgraph H and it's minimized. So let's discuss its properties. So V of H is actually, it's greater than or equal to 2k by assumption, but it's actually strictly greater than 2k. Because otherwise, think about the number of edges in H. If it was 2k, it'd be at most 2k choose 2, i.e. the number you could get in the complete graph. But if you go through that, if you plug in what the assumption was on E of H being greater than gamma times 2k minus k, well, gamma is at least 2k, and so then this is actually smaller than gamma times 2k minus k. So it's not possible. What's the point of that? Now we have wiggle room. So we know that H isn't, even though we kind of set it to be that minimum, it never actually attained that. So now we have some freedom because we could, say, delete a vertex from H and still satisfy that first assumption that H was decently large in the number of vertices. So that's exactly what we'll do. So we'll split into two cases. Case 1, the minimum degree is at most gamma. Then you take a vertex, so let's call it V of H, where the degree is at most gamma, right? Such exists. You delete it to form a new H prime. So we let H prime be this H minus V. Then V of H prime is at least 2k, so here's where we're using that fact that V of H was strictly greater than 2k. And E of H prime, well, it's going to be strictly greater than gamma times V of H minus k minus a gamma, so we'll still get a contradiction to the minimality of H there. The other case is that the minimum degree is actually then strictly greater than gamma, and hence, if you think about the minimum degree, that means the number of vertices is also at least gamma. And then E of H, now that tells us something about E of H because we know it's strictly greater than gamma times V of H minus gamma k, if you expand it out. But now take that second term, gamma k, well, we know that gamma is actually a lower bound for V of H, so we could replace that with minus V of HK. You can regroup that right-hand term and divide it by V of H to find that D of H is actually greater than gamma minus k, which was the other condition we wanted in Motter's theorem. So we've satisfied that part. The last thing to show is that H is indeed k plus 1 connected. So can we get that? Can we get that it's k plus 1 connected? So how would you do this? So maybe if you want to pause and think about it. Well, suppose not, you look at a separation of order at most k. So let's call it U1 and U2. Maybe if we were doing what standardly did be G1, G2, and the intersection is small. Then what do we know about these things? Well, let HI be the H on the UIs. So we have these two subgraphs, H1, H2. And we know that V of H1 and V of H2 is at least gamma because of the min degree condition, right? There's a vertex that's not in the cut that has at least gamma neighbors, so all the number of vertices has to be at least gamma, and the same for the other side, and that's at least 2k by assumption. Now we're almost done because by the minimality of H, right, you can look at these subgraphs E of HI made by taking kind of the left with the edges in the cut or the right kind of thing, so you get this separation. We know that E of HI is at most gamma times V of HI minus k. So we just determine that, and hence E of H is at most the sum of those two, which is then gamma times V of H1 plus V of H2 minus 2k, and then that's at most gamma times V of H minus k, which is of course a contradiction, and here we're using the fact that V of H1 plus V of H2 is, the fact that we're only double counting k vertices because V of H intersect V of H2 is at most k. So it's a very slick proof where you just kind of set up the right formula, right? You choose a maximum graph in just the right way. And then it's kind of a little strange to do these conditions, But that's in spirit also what goes into kind of the Kostatchka-Thomason or Bollabas-Thomason results, and it'll also go into some of the later results we talk about. This kind of proof method of choosing a maximal object in just the right way. Now, let me do another question that also kind of goes in this line and has history. So we've determined that average degree forces, large complete minors, large complete subdivisions, large connected subgraphs. You can actually ask about chromatic number. So does a graph of huge chromatic number contain a subgraph of large chromatic number and large connectivity? So obviously it contains one of large chromatic number because it's already huge. It also contains one of large connectivity because they'd have high, average degree, and so then they'd have large connectivity by monitors, but can we get both at the same time? And so the first result along this line was by Alon, Kleitman, Thomason, Sachs, and Seymour, who showed in 1987 that if chi is at least on the order of k cubed, then you can get a k-connected subgraph with chi at least k. So that's what I mean, going from huge to large for both. And so that's a very nice result. This was followed up by a result by Chunovsky, Penev, Scott, and Trottignon in 2013, which actually lowered this that omega of k squared suffice. And then this was finally improved by Girard and Arianin just this year, that for every positive integer k, if G is a graph with chi at least 7k, then you can get a k-connected subgraph H with chi of H is at least chi of G minus 6k. And so in particular, that would say that, 7k is enough to get you k and k. So you can get linear in k. So that kind of completes that sequence of research. But also it more mirrors the result from Motter, that just as Motter, you could even have higher density, but you could just trade something linear in k to get a k-connected subgraph of still decent density. You could do that with chromatic number now as well. And the proof of Girard and Aronian is also very much from the book. It's take kind of a minimal kind of non-colorable object with certain parameters and show that it has high chromatic number and high connectivity. So in spirit, a bit like Mahler's proof as well. But let's not go through that. And let's move on. So kind of going back to a question we saw last time with the graph minor structure theorem, it goes more like this. So now this is a little more structural, we asked about the disjoint paths problem. So fix k and let S1 to Sk, T1 to Tk be vertices in a graph. When did there exist these k internally disjoint paths? Well, let me go something stronger. Let's call a graph k-linked if no matter how you have this set of vertices, S's and T's, you can always find these paths. So if instead of asking, when can we decide or such, as in the disjoint paths problem, let's just call a graph k-linked if you can always do this. And so here's a picture, the S's to the T's, and again, they could be really the same vertices, but here I've drawn them disjoint. So note though that k-linked implies that you're k-connected, right? So Menger's, or the definition of k-connected is if I have these set S's and T's, I can get the paths, but I don't necessarily get them in the right order, the S1 to T1, etc. K-linked is that, but plus the order condition. So you might ask, does some converse hold? Right? So naturally, kind of k-connectivity is a requirement for k-linked, and does some converse hold? And the answer is yes. So what a level of connectivity implies linked? So there were, again, a number of earlier results we don't have time to go through, but there was this breakthrough by Bollabas-Thomason in '96 who showed that a linear function suffices. So in the spirit of Motter or Girard and Aronian, that again, somehow linear for these questions is the right answer. So if a graph G is omega k connected, then G is k linked. Their number was around 22, which is not so large. The best bound to date is 10k by Thomas and Wolin from 2005. So a very fundamental question, but if you don't care about the exact value, just kind of the right order up to some additional constant, if you're willing to pay a little bit more, we can actually get this k-linked property. And I think that's a very nice fundamental result in connectivity. And so that's very nice. The Girard and Aronian, where we can trade a little bit of chromatic number to get connectivity, or Motters, where we can trade a little bit of density to get connectivity. So all kind of go together as nice results. Let me spring another one on you, which is more recent. So we'll call a graph woven, so here AB woven, if I have for every three sets of vertices, R, which will be R1 up to RA, S, which we'll say is S1 up to SB, and T, T1 up to TB, so I can get a KA model, so that's a complete minor, but a model rooted at R. And what would rooted mean is that every vertex from R, each of the R's appears exactly in one of the parts of the model. And I can still get a set of internally disjoint paths. So here's a picture. So I can get the linkage from the S's to the T's, while also building a minor that's rooted on those subgraphs, they're rooted on those vertices, the R's, and is otherwise disjoint from the linkage. So, you know, it's asking kind of for more. Can I always not only build a linkage, but can I build kind of complete minors as well? And surprisingly, there's a very nice theorem of Noreen and Song from just last year that says that if you're high enough connected, you're AB woven. So if G is omega A root log A plus B connected, then G is AB woven. So think about what that means. If A is 0, then this is just the Bollabas-Thomason theorem, that if you're omega B connected, you're B linked. But if B is 0, this is in spirit of the Chromatic-Thomason result, that if you had A root log A connected, then you'd kind of be able to find not only minors, but rooted minors. And so, and uses, indeed, this theorem is a combination of those theorems, using results from Bollabas and Thomason, but also the Chromatic-Thomason bounds as a black box. But you can really do both. So I think that's a nice new theorem, and it'll have applications when we talk about Hadwiger's conjecture in the next lecture. So there's that concept. So these are all very nice. Now let me turn to kind of a more general question, back to minors, right? And so here's a very nice question. When does a graph of density little d have a minor of density big D? Right? So if we have a graph that has kind of small density, can we still find a minor of maybe much larger density? Is kind of a natural, you know, question. So what's the obstruction to doing this? So this will be quite useful if we want to build KT minors, because we know that T root log T density suffices. So if we could kind of find the T root, if big D was T root log T, this would be helpful. And then it turns out there's an obvious obstruction to this. It's small graphs, namely that if the number of vertices is strictly less than big D squared over little d, there's just not enough edges, right? Because then the number of edges would be also kind of on the order of d squared, big D squared, or really less than that, and so there just won't be enough edges to find such a minor. You might think that's the only obstruction, but of course you can take the disjoint union of such graphs. So you can just have lots of little small graphs, and you won't be able to contract if it's the disjoint union and find kind of denser graphs. But is this the only obstruction? And the answer is, in spirit, yes. So here's a very nice theorem. It says that for all S, there's some G of S, which we'll talk about what it is. I haven't defined it yet. But such that if I have a graph of density, say, 0, and we let big D be S times little d, then either you can indeed find a minor, that's case 1 there, with density at least big D, or I can find a subgraph that's pretty small. So that's at most kind of what we expected, the big D squared over little b times this G of S, and whose density is also pretty big as well. So density at least little d, but over G of S. So think of G of S as an error term, saying how much we have to pay, both in the size of the subgraph and its density. But if it's low, then actually we're kind of finding a small, dense subgraph, which is really kind of the main obstruction. So what is this G of S? Well, Noreen and Song last year showed that it actually exists, and they showed S to the alpha for any alpha b 0.7. I improved this to S to the alpha for any alpha greater than 0. So that's quite nice. Basically, so you have very little error term, and I got some function that was like log S to the 2/3, but then this year it was improved to 1 plus log S to the 6th. So you can kind of get a polylog error term in this kind of density increment theorem. So it's reminiscent of other theorems where you're trying to improve the density, but here it's in relation to minors. So when can you kind of find minors of larger density. Really, this is the obstruction. Let me continue along this line and relate it back to some earlier research about minors in large girth that's quite nice. So Kuhn and Ostis in 2003 showed the following, that if G has girth at least 5 and average degree at least omega tilde t to the 2/3, then G contains a KT minor. So Bollabas-Thomason said T root log T was needed, but actually if you impose further conditions, so high girth, so exclude triangles and 4 cycles, you can get it down to T to the 2/3. Except what's that tilde? It's hiding polylog terms. So now that's quite nice. So really you need kind of much lower average degree if you impose the girth at least 5 condition. And their proof, I won't go through, is not too long, maybe a page or two or something that uses some nice random ideas. But I'll relate this back to the density increment theorem from the last slide, because it actually follows from that. So if we let big D be T root log T on the order of, then by the density increment theorem, either we can get a minor of density big D, so that's our target density, and hence we'd have a KT minor by Kostachka and Thomason, or there'd have to be a small subgraph. What does small mean here? There'd be a subgraph H of G with V of H being, again, big D squared kind of over little d, which is, T squared over T to the 2/3 is roughly T to the 4/3, but with some polylog terms there. And we'd have minimum degree at least, really average, but we could then pass to minimum degree. That would give us on the order of T to the 2/3, the original degree, again hiding some polylog terms. So if we pack enough polylog terms, this will go in our favor, and we'll find a subgraph which has kind of minimum degree kind of some number, and the number of vertices is the most square of that number. And that's a contradiction since H is a subgraph of G, which has girth at least 5, right? If you have a girth at least 5 graph, say, and had minimum degree D, then you'd look at all the neighbors, then all of their neighbors also have to be disjoint. You'd have to get the number of vertices being at least kind of, D squared plus D plus 1, and that would be a contradiction here. So that's maybe a nicer way to think about their theorem fitting in the context of this density increment theorem. In a similar vein, they proved that if G has no KSS subgraph, an average degree at least some function here, then G contains a KT minor. So the first theorem is if you exclude KT2, really a C4 subgraph, also C3, but that turns out not to be important. But more generally, if you're willing to exclude KSS subgraphs, then it turns out that you can have kind of average degree that's a little bit smaller than T, so to some power, then you'll contain a KT minor. That we could also go through, would also follow from density increment theorem if you knew things about minimum degree and subgraph, but let's not do that. Importantly, these results of Kuhn and Ostis showed that the famous Havdegger's conjecture holds for graphs of girth at least 5, and more generally, graphs that avoid certain subgraphs. So that'll lead us into our next lecture, where we'll discuss Havdegger's conjecture and things that are known about it. But today we've talked about a summary of various results on minors. So what's the right average degree to force a large minor or large subdivision? Does average degree lead to high connectivity, high connected subgraph? Motter's theorem, yes. So we went through that. We went through this Girard-Nuryanin theorem, where we want high connectivity and high chromatic number. We went through the linked theorem, which is very nice that indeed, you can get omega k connected implies k linked, which actually also implies the Bollabas-Thomason theorem, because if you're k squared linked, then of course you can find the paths to kind of make a KT subdivision. So that was the tie-in there. And then we talked about woven and then moved on to this density increment and minors and large girths. So they all kind of stemming from questions that seem quite natural. When can we force structure? Or the converse questions, or contrapositive questions where, what if I exclude this, then what's the most I can get? Most edges, etc. So this will all tie into next week when we talk about extremal graph theory, because these are really questions in extremal graph theory as well about minors and subdivisions and such. But I hope you've enjoyed this lecture. Until next time, see you then.